two pictures of the same math problem. On the left, three translucent planes in three dimensions meeting at a single point. On the right, three vectors scaled and added, landing on a target. They solve the exact same system of equations, but one of these pictures becomes useless the moment we step into four dimensions. Which one and why? Let's build both pictures and find out. Here's our system. Three equations with three unknowns. Equation 1, 2x minus y equals 0. Equation 2, negative x plus 2y minus z equals negative 1. Equation 3, negative 3y plus 4, z equals 4. We can organize this neatly as A times x equals B. The coefficient matrix A has rows 2, negative 1, 0, then negative 1, 2, negative 1, then 0, negative 3, 4. Each row of A holds the coefficients from the corresponding equation. The unknown vector x is the column vector xyz, and the right-hand side vector b is 0, negative 1, 4. Remember, in two dimensions, each equation defined a line, and the two lines met at a point. Now we go one dimension up, where each equation will define a plane in three-dimensional space. In three dimensions, a single equation with three unknowns defines a plane, a flat sheet extending infinitely in all directions. That one equation has infinitely many solutions, and all of those solutions live on that plane. Now add a second equation. This gives us a second plane. Two planes typically intersect along a line. So we still have infinitely many solutions, but now they are confined to just one dimension and that line of intersection. Finally, add the third equation, which introduces a third plane. Three planes typically meet at a single point. That point is the one and only solution to the system. For our specific system, here are the three planes. The blue plane represents the equation 2x minus y equals 0. The orange plane represents negative x plus 2y minus z equals negative 1. And the green plane represents negative 3y plus 4, z equals 4. These three planes intersect at exactly one point, x equals 0, y equals 0, z equals 1. Let's verify this solution. Plugging into the first equation, 2 times 0 minus 0 equals 0, check. Plugging into the second equation, negative 0 plus 2 times 0 minus 1 equals negative 1, check. And plugging into the third equation, negative 3 times 0 plus 4 times 1 equals 4, check. That glowing dot is our solution, and the row picture is visually satisfying in three dimensions. But keep this in mind. It only works because we can draw three dimensions. For higher dimensional systems, we'll need a different approach. Now, same system, but a completely different picture. This time, take each column of matrix A and write the system as a vector equation. The first column of A is 2, negative 1, 0, shown in blue. The second column is negative 1, 2, negative 3, shown in orange. And the third column is 0, negative 1, 4, shown in green. Now rewrite the system as x times the vector, 2, negative 1, 0, plus y times the vector, negative 1, 2, negative 3, plus z times the vector 0, negative 1, 4, equals the vector 0, negative 1, 4. This is what we call the column picture, a linear combination of the columns of A. A linear combination is simply a sum of vectors, each multiplied by a scalar. In other words, scalar times vector plus scalar times vector, and so on. So the question becomes, what scalars x, y, and z do we need to combine these three column vectors to produce the right-hand side vector b? Look at the right-hand side. B is 0, negative 1, 4. Now look at column 3, 0, negative 1, 4. They're identical. So we need 0 copies of column 1, 0 copies of column 2, and exactly 1 copy of column 3. Let's verify. 0 times the vector, 2, negative 1, 0, plus 0 times the vector, negative 1, 2, negative 3, plus 1 times the vector 0, negative 1, 4, gives us a 0, negative 1, 4. That's exactly B, confirmed with a check mark. The solution reads off immediately. X equals 0, Y equals 0, Z equals 1. Same answer as the row picture. In the diagram, only the third vector lights up. It lands directly on B. We can write this compactly as B equals 0 times column 1 plus 0 times column 2 plus 1 times column 3. Now let's change B to the vector 1, 1, negative 3, and see if the column picture still delivers. Column 1 is the vector 2, negative 1, 0. Column 2 is the vector negative 1, 2, negative 3. We add them component by component. For the first component, 2 plus negative 1 gives 1. For the second component, negative 1 plus 2 gives 1. For the third component, 0 plus negative 3 gives negative 3. That gives us the vector 1, 1, negative 3, which is exactly our new B. So the solution is x equals 1, y equals 1, z equals 0. One copy of column 1 plus one copy of column 2, placed tip to tail, lands right on B. Here's the key insight. Let's compare how the row picture and the column picture hold up as we increase the number of dimensions. In 2D, the row picture shows lines intersecting. That works just fine. And the column picture asks us to combine two vectors. Also works great. In 3D, the row picture shows planes intersecting. It's doable, but already getting harder to visualize. The column picture, still just combining three vectors, no problem. Now move to 4D. In 4 dimensions, each equation defines a 3-dimensional hyperplane, a higher dimensional analog of a plane. Try drawing that. The row picture breaks down, but the column picture still just asks, can I combine 4 vectors to reach B? Works perfectly. And in n dimensions, the row picture is completely hopeless. We simply cannot visualize it. But the column picture always asks the same elegant question. Can I combine these n vectors to reach B? Whether those vectors have 3 components or 3,000 components, the idea is identical. The conclusion is clear. The column picture wins because it scales to any dimension. The row picture does not. The column picture is the doorway to modern linear algebra. Let's see why. Span. The set of all vectors you can reach by combining your columns. Linear independence. Whether any column is redundant, meaning it can be written as a combination of the others. Column space. The collection of all right-hand sides B that the system can actually solve for. Rank, which tells you how many truly independent columns you have. And null space, the set of all solutions when the right-hand side is 0. All of these are column picture ideas. Every one of them flows naturally from thinking in terms of column vectors. Now the row picture gave us beautiful intuition in 2D and 3D. Don't forget it. It clarifies intersections, parallel planes, and the degenerate cases. But the column picture is the one that keeps working in every dimension. Both pictures solve the same problem today. Only one comes with us to higher dimensions.